Hello, it's Keith here, and this is lesson 5 of my 6502 assembly programming tutorials. Now, over the last few weeks we've been covering various mathematical commands, but we've not come to the end yet, and one thing we've been overlooking is the commands to work at the bit level. In 8-bit mathematics, there's going to be a lot of times where we want to work with the individual bits within our registers. This could be because we're sending data to or receiving data from various hardware, and those bits will have different meanings, but also in general mathematics, it's much more easy in some cases to work at the bit level, and so we're going to have a look at various ways to do that today. To start with, I want to discuss the AND, OR and EOR commands. Now, what are these? Well, these are logical commands where we take a parameter and we apply that parameter to our accumulator, and depending on each bit within the parameter and the matching bit in our accumulator, the result will vary. So I think it's going to be clearest for us if we look at this truth table here. So if we look at this table here, you can see, if you imagine that this first column is the accumulator, the second column is the bits in our parameter, and the third column is the result of the combination of the parameters with the respective command. So what happens in the case of the AND command? Well, the clue should always be in the name of the command, and in the case of the AND command, the result will be 1 where the input of both parameters was 1. So if the accumulator and the parameter were 1, the result will be 1, otherwise the result will be 0. So 0 is false and 1 is true effectively. So what about the case of OR? Well, if the accumulator is 1 or the parameter is 1, then the result will be 1, and you can see that here. The only case that an OR command will return in a 0 is if both parameters were 0. Now, EOR is a bit different. EOR is sometimes called XOR. It was known as XOR on the Z80, but the 6502 calls it EOR, and this is known as an exclusive OR. And what this does is it inverts the bit in the accumulator when the bit in the parameter is 1. If the bit in the parameter is 0, then nothing happens. So if the accumulator is 1 and the parameter is 1, the result is 0. If the accumulator is 0 and the parameter is 1, the result is 1. But if the parameter is 0, then the result will be exactly the same as was passed in the accumulator. So how can we use these? Well, the most common use of these will be where we have a value in our accumulator and we want to set some of the bits high or low or flip those bits. And what we do is we set our parameter according to what the result we want to be. So if we want to remove some of the bits, effectively setting them to 0, we can use an AND command, and the bits that are 1 will be kept and the bits that are 0 will be lost. You can see here that the last 4 bits have been set to 0 because the last 4 bits was 0 here. An OR command works the other way. If we want to set some of our bits to 1, we just put them as 1 in our parameter to the OR command, the OR command as it's called in 6502, and the bits that are 0 in the OR parameter will be left unchanged, but the bits that were set to 1 will be set to 1. Now EOR will flip the bits, so the bits that are 1 in the parameter will be flipped, the bits that are 0 will be unchanged. So there we go. Now, it's too premature to do this in our 6502 series, but in my Z80 series at this stage, I demonstrated how these various commands would apply to a 1-bit bitmap on the screen. So if we had the test text here, and then we applied an EOR, then the bits that were 1 would be inverted, the bits that were ANDed would be kept, and the bits that were ORed would be replaced. So you can see OR is effectively applying a new layer to the preceding graphics. The AND would be removing part of the previous graphics, and EOR would be inverting part of the previous graphics. And EOR, of course, is known as XOR, and XORing is a crude way of applying sprites to the screen, where applying the sprite twice will clear it off the screen, but it will corrupt anything that's already on the screen underneath it. But as I say, we can't do that at this stage in the 6502 series because we're covering so many different systems on the 6502. Anyway, let's actually try these commands in some sample code. So I've got some sample code here. So we're going to set this sample bit combination into our accumulator, show it to the screen, and then we're going to do the AND, the OR, and the EOR just as described. So let's see what actually happens. So we're going to use the nest this week. So you can see here, we're showing this bit combination here to the screen. Then we're using the AND command, and we're only keeping the top 4 bits because the top 4 bits are 1. So you can see the bottom 4 bits have been wiped to 0 and the top 4 bits are retained. Now next we're setting the bits back to the way they were, and we're using the OR command. In all of these cases you can see we're using a percentage to specify a combination of bits because that's how our assembler works. So then we are doing our OR command here, and you can see that where the top 4 bits were ORed in with 4 ones, we can see those bits have been set to 1. The bits that were 0 in the OR mask are unchanged. Finally, EOR, our XOR command, the top 4 bits were 1, and you can see these bits were flipped. The bottom 4 bits were 0, so they've been unchanged. And you can see here how the AND or EOR command affect the bits within our accumulator. Of course, you can download this example from my website and change it if you don't understand how these commands are working, and just see what effect it has on various combinations of the bits. So that's how we can actually remove or keep or invert various bits within our accumulator. Now, one thing you're going to need to do quite a lot in programming is to shift bits around within our registers or within our 0-page entries. The reason we are going to want to do this, for one reason, is, as I've said before, we don't have any multiply or divide commands within our 6502 processor, but a very easy way of doubling and halving numbers is to just shift all the bits to the left to double them, or shift all the bits to the right to halve them. If you think about it, bit 0 within our accumulator is worth a value of 1. The bit to the left of that is 2, the bit to the left of that again is 4, and so on. So every time we shift a bit to the left, we're effectively doubling it. And so this is a reason why we might want to use our mathematical commands for multiplying and dividing. The other reason is, let's say the top nibble of a byte has a particular meaning and the bottom nibble has a different meaning. For example, maybe this is some data we want to pass to one of our pieces of hardware, or we've received from some of our hardware. Well, we can mask out those bits we don't want with an AND command, and then maybe we want to shift those bits to the right, so we can use them in a lookup table or something like that. We need to be able to shift those bits around, keeping the same combination of bits, but having them in a different position within our register. And on the 6502, we can use the rotate commands to rotate bits around, and arithmetic and logical shift to shift them around. What's the difference between a rotation and a shift? Well, on the 6502, a rotation uses the carry flag. Now, if you remember before, the carry flag is used as an overflow for addition and subtraction, and it's also used for comparison commands when we're comparing the accumulator to another value. Well, with rotation, if we rotate all of our bits to the left, then the bit that was in bit 7 will be pushed out of the accumulator, and what will happen is it will go into the carry flag. At the same time, bit 0 will become a new bit because all of our bits have been shifted to the left, and that will be filled with the previous value of the carry flag. So effectively, the carry flag becomes the 9th bit in a rotation of all of the bits within our accumulator. Arithmetic and logical shift don't do that. They still shift to the left and the right. However, any bits that are pushed out of our accumulator are simply lost, and any new bits that are formed within on the opposite side of the accumulator will be a 0. Let's see that in action, and I think it'll be a lot clearer what they're doing. So in this example, we're going to use a command called monitor bit C. This is a subroutine I've written. It's going to show the contents of the accumulator in bits, and it's also going to show the contents of the carry flag. What we're going to do is we're going to define this pattern, which I think will show quite clearly what's happening. We're going to clear the carry flag because the rotate command uses the carry flag, and then we're going to try each of the commands one after the other and see what they do. We're going to rotate a total of 9 times because there are 8 bits within our accumulator and there's 1 bit in our carry flag. Let's see what happens when we rotate left. So you can see here, this is the starting situation of our accumulator, and our carry flag was 0 because we cleared the carry here. So first we did a rotate left, and you can see here that this bit that was here in bit 7 has been pushed out of the accumulator and has actually been pushed into the carry flag. At the same time, a new bit has appeared here, which is bit 0, and that was actually the original carry here. You can confirm that because if you look at the next shifting of left as we loop over here, you can see we did the same again. This time this bit was pushed into the carry, and the original carry, this bit 1 here, was actually pushed to here. And you can see here that these are moving all the way along, and all of these bits that go off this side here are coming back here, and the end result is that on the 9th iteration of this, we're actually in the exact same position as we were here. And that proves that we were rotating around because we are rotating all the bits, and if we do a full rotation we end up in exactly the same situation as we started. That's what the rotation does. Now what about if we rotate right? Well, it's pretty obvious what's going to happen now. So the procedure is entirely reversed. So you can see here, this is our starting pattern, and as we shift right, one of these bit 0s gets pushed over to this side into the carry, and we don't really see anything into the carry until we get this bit here pushed over to the right, which then forms in the carry, and then this bit is pushed to the right and ends up here. Again, this bit is ending up in the carry. But again, you can see in exactly the same situation, the final result is the same as the starting point. Because it's a rotation, everything is just moving around and nothing's getting lost. So that's rotate left and rotate right. So what about arithmetic shift left? Well, let's take a look. So here's the arithmetic shift left, and it becomes pretty clear fairly easily what the difference is. So at the start, everything looks pretty similar here, and we've rotated to the left, and the value 1 has been pushed into the carry here. But then when we shift left again, rather than the 1 appearing on the other side, nothing appears on the side. All of the bits are 0. And no matter how many times we shift left, and no matter how many ones are pushed off this side here, the result that's added to the right-hand side, the opposite side of the shift, is always 0. So in the end, we just end up with a 0. So you can see here that the logical shift, while it's moving all the bits to the left, anything that is pushed off the end of the accumulator is simply lost. And this is why it's called an arithmetic shift, because we're doubling the numbers, but we wouldn't want them to come back on the other side, because if we're shifting an 8-bit number, really the extra bits should be pushed into a following number. Now, of course, we can take advantage of this, and we can rotate the extra bits that were pushed out with the arithmetic shift left into a 0-page register using the rotate left command, and this will pull those bits that were pushed out of the low byte into a high byte, and in this way we can create a 16-bit pair and rotate the bits throughout them. So what about logical shift right? Well, let's try it now. Well, you can probably guess what's going to happen, and you can see here. So as we're pushing along, again, there are bits being pushed off the right-hand side, and they're ending up in the carry flag here. But in the same way as arithmetic shift left, logical shift right, any bits that are lost are never returned. So eventually, again, we end up with all zeros here. And that's the difference between the rotate commands and the logical shift commands. The logical shift commands are filling any extra bits with 0, and any bits that are pushed out are lost. The rotate commands are using the carry to store any bits that are lost, and any bits that are added are taken from that carry. Now, if you're familiar with the Z80 or the 68000, you'll probably be a bit frustrated that those are your only commands on the 6502. You may want a command that rotates the bits within the register without using the carry flag, and you may want to be able to push 1s into the missing bits rather than 0s. Well, the only way we can do this within the 6502 is to kind of simulate those commands, and so I just want to give you a few ideas of ways that I've used to simulate the commands that are missing. So what about if we want to shift the bits, but rather than adding 0s in the new bits, we want to add 1s? Well, the simplest way to do that is just to set the carry before we do our rotation, and you can see that just here. So because we're forcibly setting the carry before each rotation, every bit that's added is now a 1. That's very straightforward, and of course we can do that rotating right or rotating left. But what about if we want to rotate the bits within the accumulator without using the carry? Well, there's a couple of different ways we can do this, but the simplest one that I'm using here is just to use the pushing of the accumulator. If you think about it, if we back up the accumulator, we rotate in the direction we want, then we will then get the top bit of the accumulator. We then restore the accumulator to its original state, but the carry is still set of that top bit. We then do the rotation again, effectively putting the bit that we just pushed out of 7 back into position 0. So we are using the carry, but all of the 8 bits are the same 8 bits as we had originally. So let's just run that now. So you can see here that we've rotated around, but you'll notice now as soon as a bit gets pushed off this side, it immediately comes back on this side. And the result of this is that rather than taking 9 iterations for a full rotation, it now only takes 8. So you can see here that we are effectively rotating without the carry just by using these commands. Now, I should point out that this isn't necessarily the best way of doing this kind of command, and there are a lot of other ways, and I'm trying to document them as I learn them, or at least figure them out. On my website, there's a section called Important Commands That Don't Exist, and here I'm kind of describing commands that other systems have that don't exist on the 6502, and possible ways you can simulate them. For example, the Game Boy Z80 swap command, where you swap 2 nibbles, can be done by a combination of arithmetic shift lefts and add with carries and rotations. Quite complex, but it does work. And rotate left and rotate right with wrap on the Z80 can be done with the kind of commands I've just described here, and there's also an alternate way of doing it here. So please check out my website for all of the best ways that I've figured out so far, and if you know a better way of doing what I've described here, please just let me know and I'll put it in there. So we now know how to use masks to remove or force bits to be set, or to flip them using AND, or EOR, and we also know how to do rotation and logical shifts. Well, what else do we need to know about bits? Well, one thing we will want to do quite a lot is things like bit testing. This is where we want to check if a single bit within a register is set. An important time I needed to do this quite a lot is with my joystick code. My joystick code uses a single byte, and a different bit in that byte will represent up, down, left, right and fire. So I want to test that to see what fire buttons are being pressed and what are the buttons, and then jump to the code that's going to handle that. One option would be to use an AND command with a single bit that's positive within the parameter of the AND command, and then jump based on that command. That will work fine. However, the disadvantage of that is that AND command will alter the accumulator. Now, we might want to do a set of branches depending on different bits, and we might want the accumulator to stay the same throughout that procedure. How can we do that? Well, what we can do is use the bit command on the 6502 to do this. What the bit command does is it takes a single address either in the 0 page or within our main memory, and it will look at that address, take a byte, and it will simulate an AND of that byte with the accumulator. It will set the flags accordingly, but it will not change the accumulator. So we can use this, and then we can do a branch based on those flags, and we can jump to our code accordingly. So unfortunately on the regular 6502 this command can't work with an immediate parameter, i.e. a fixed value like you see here with a hash at the start. It can on the 65C02, which is the more advanced processor in systems like the Atari Lynx, but we're not going to cover that today because I want to show you things that will work on all of our systems. What we're going to do is we're going to define 8 bytes in memory defined by labels called T-bit. When we want to define a fixed byte, we use dB to define the byte. And you can see I'm using a % here to define it in binary. And you can see we're just shifting the bit along to define bits 0 to 7 set to true here. And then we can use these with our bit command to do the comparison. I should point out this isn't very efficient. The address T-bit is a 2-byte address. The bit command is a 1-byte command, so this is using 3 bytes. So in this example, we're actually using more bytes than the AND command. This is just an example. If you really wanted to save memory on this, then you would probably want to try and put these in your 0 page, because then you would only be using 2 bytes for the command. But as I say, I'm just trying to show you how the command works. So what we're going to do here is we're going to do a bit test. We're going to test bit 1, which is this bit here, with this parameter. And if the value is not 0, we're going to jump and show an A. Otherwise, we're going to show a B. We're also going to show the contents of the accumulator just to prove it's not been changed. So you can see here we've returned a B, and that's because the value of this bit 1 is a 0. And of course, if we change this to bit 0 here, we're now using this bit mask here. And if we run it again, you can see we're now showing an A because bit 0 is 1. Of course, if we change this to a branch of equals, then we will be effectively jumping if the bit is 0. And you can see we're now showing a B. So there we go. So that's how we can use the bit command with a memory address with a defined bit mask there. Now on the 6502 the bit command isn't as efficient as the Z80 equivalent because it does take up more memory, but there is one surprising advantage of the bit command, and this comes if you're testing various bits. Now whenever you do a bit test command, the 0 flag is set according to the parameter you used with the testing command. However, at the same time the negative and overflow flags are set according to bit 7 and bit 6. And this means if you want to branch depending on the value of bit 7 and bit 6, you can do any other bit test command, and then you can immediately use branch plus, branch minus, or BVS and BVC to branch depending on the contents of bit 7 and bit 6 of your accumulator when you did that original bit test command. That's a bit of a quirky advantage, but if you're really trying to optimize your code, it's something that people do use. So there we've covered a large variety of commands that will allow us to deal with bits within the 6502. Now there's one other command I want to cover today. It's not relating to bits, but it's a fairly common and simple command, and I think it's time we covered it. It's called the no operation command, NOP. And what it does is absolutely nothing. Yes, you heard me right. It doesn't do anything at all. Now, what's the point of a command that does nothing? Well, the first thing you can use it for is you can use it to add a small delay. If you want to have your code slowed down because it's running too fast, you can just put some no-op commands in and you can pad out your code and it will slow things down because it still takes the processor some time. More useful cases for it are for debugging and for self-modifying code. Now, if you're using a monitor, which is a piece of debugging code that can actually show the contents of your code as you're working, you might want to disable part of your code because it's faulty or because you just want to disable it. So you could replace a jump command with 3 no-ops, for example, and this will turn the code into non-functional code, and then you can test the rest of your code with that removed. A more practical case that we will look at later is self-modifying code. This is where your program changes parts of itself as it's running. It's a lot faster because you can make your code, rather than having a condition, have a jump, and you change the jump to different positions. But what about if you have a piece of code that, say, adds 1 to the accumulator in one iteration, but later on you want to make it do nothing? Well, what you can do is you can replace that command with a pair of no-ops, or the number of no-ops that are needed to overwrite that command. So it can be used for delays, and it can also be used for various ways of modifying code and disabling parts of that code accordingly. Anyway, let's have a look at the command. So here we've got a loop. We're going to loop around this 255 times, and then we're going to print an A, and then we're going to repeat the entire procedure again. We're using 4 no-ops here, but even then it's not slow enough to make this viable to see on the screen. So we're going to loop around these 4 no-ops 255 times. So let's run it and see what happens. So you can see here, we can see the A's gradually drawing to the screen. Well, what happens if we increase this from 4 to 16 and run again? It's much slower, and that's really the only point I'm trying to make at this point. No-op commands will take up some of the CPU power. They are a single byte command. As I say, they have more practical uses than just slowing things down, but that's just a case I wanted to show them being used for today. Of course, this is fairly inefficient. What you would actually probably want to do is have a nested loop where you were using X and Y simultaneously to make things a bit slower. Or of course you might want to use interrupts or something like the firmware to slow the system down, rather than this fairly crude way of slowing your processing down. But as I say, this is just a simple example of what the no-op command does, or in the case of a command that does nothing, doesn't do. Anyway, that's all I wanted to cover today. As always, you can download the source code to these examples from my website. There's the text version on the website as well. I hope you've enjoyed this. Thanks for watching today, and goodbye.